The next presentation is by Dr. Markus Müller. I will give you a short bio of him. Dr. Müller is group leader at the Institute for Quantum Optics and Quantum Information in Vienna, Austria, and a member of the Austrian Academy of Sciences. He is also a visiting fellow at the Perimeter Institute for Theoretical Physics in Waterloo, Canada. Prior to these appointments, Dr. Müller has been an assistant professor and Canada Research Chair in the Foundations of Physics at the University of Western Ontario in London, Canada. He received his doctorate from Berlin University of Technology in 2007 with a thesis titled Quantum Kolmogorov Complexity and the Quantum Turing Machine under the supervision of Professor Ruedi Seiler. Dr. Müller has over 50 technical publications to his name. Markus, over to you.
Okay, thank you so much, Bernardo, for introducing me and for inviting me. So my name is Markus Müller. I'm a group leader at the Institute for Quantum Optics and Quantum Information in Vienna. And I will now talk about some puzzles and enigmas from physics and why I believe that they motivate some, broadly speaking, idealist worldview. Not one where consciousness plays any direct role, but some mathematical or structural version of idealism, perhaps. So I will begin with a few puzzles and enigmas from physics, and I will try to argue that they really motivate us to take an idealist approach to physics in some sense. This will be the first part of my talk. In the second part, I will present one possible way to formulate such an approach, in which, in some sense, the first person is fundamental and our notion of external world is emergent. And then if I have some time in the third part, I will demonstrate how in such an approach, objective reality is in some sense an emergent phenomenon, a statistical phenomenon. And that will involve some quite surprising phenomena. For example, there's a probabilistic version of Wittgenstein zombies here and other surprises. We'll see if we get there. So let me begin with the first part. Here's a thought experiment that has appeared in the philosophy of the mind and philosophy of physics in several ways. Parfit's teletransportation paradox. So imagine you're this guinea pig, and every morning you have to go to your workplace on Mars. So what you do is, like in a science fiction movie, you enter a teleporter, and then the teleporter immediately scans you, destroys you, and rebuilds you on Mars. This is very handy. But then one day something terrible is happening. So your teletransporter is compromised by a hacker. And this means that yes, there will be a copy of you going on Mars, but somehow another copy that stays on Earth. Well, suppose now you're the guinea pig this morning and you know that your teletransporter is compromised. And so before entering this transporter, you ask yourself, well, what's happening to me? So will I end up on Earth? Will I end up on Mars? Or how should I even think of this? So what will I see next after I enter this teletransporter? Here's another problem or puzzle from physics, in fact, from cosmology. It's known as the Boltzmann brain problem. And here's a cartoon of it. So suppose you have a model of cosmology of the universe, which is really large. And it's actually combinatorially large. And so what you then have is, every once in a while in the world, out there, you have some thermodynamic fluctuations or statistical fluctuations. And just by pure chance, because the world is really, really large, some of these fluctuations will be like you. It will be what's called the Boltzmann brain, some kind of brain coming into existence that thinks it has led this life on Earth, like the actual guinea pig in the picture. But has just appeared by random chance. And perhaps in the next moment, it will realize that something's really weird and it will disappear. So now suppose you know that your universe is of that kind and you think you're standing here on your planet. How should you think of that? Should you believe that you could be perhaps one of these strange fluctuations out there in space, one of these Boltzmann brains, or not? So you may also ask yourself, well, given what I know, what should I expect to see next? And now I've given you this kind of cartoon pictures, but this is really serious thought experiments. So the cosmologists write papers about something like this because they want to use thought experiments like this to exclude some of their models. They sometimes want to say, good, here is a model of the world which involves inflation, for example. That model predicts a lot of these brains in some sense. And so isn't that perhaps then already excluded empirically, because we haven't disappeared so far? So maybe you can use this kind of reasoning to exclude some cosmological models. But it's really unclear how you should think of that. So and there's a lot of discussion and debate what to make of problems or thought experiments like this. So here are the two problems that I've so far presented to you. You can think that they are of some kind of exotic regime. These are really exotic thought experiments that we do not usually think of having any impact on everyday life. Another one would be if we ask, for example, in the philosophy of mind, what happens if you simulate a human agent on a computer? Perhaps we promise this to a human, hey, we will in the future simulate you. What should this human believe that he will see later on? So will that human, he or she, wake up in the simulation, yes or no? So these are other philosophical discussions that are in some sense centered around this question, what will I see next? There's also the hard problem of consciousness, but I cannot really say and will not really say much about that because my talk will not be on consciousness in any way. But certainly there's a less exotic regime where we ask this question every day, what will I see next? For example, laboratory experiments. So if our famous guinea pig just builds up an experiment on an optical table and asks whether it will perhaps see this detector click later on, yes or no, then this is also a question of that kind. But it's one where we think we know the answer. Another question, which is a bit different, but still kind of the empirical regime, would be to do astronomical observations and to guess what we will perhaps see when we look up in the sky. So these are instances of this question, what will I see next, that come from the empirical regime. And now typically we think of, in this regime, physics applies. Physics tells us what we should expect to see in our laboratory experiments or in astronomical phenomena. But in this exotic regime, it's not so clear. It's perhaps the philosophy of mind that tells us what we should do there. Or maybe some of these questions are not, we don't even want to ask them in the first place. That's a reaction that also sometimes comes to mind. But wait a second, so something's wrong. So you cannot really have this strong separation to the two regimes, because this Boltzmann brain problem, that's kind of an exotic question, has really appeared in physics. So then the distinction between the exotic and the empirical regime cannot be that sharp. There's some common ground to both of them. So, well, you see, okay, well, isn't here one particular difference from physics and philosophy? So I phrased this question, what will I see next? Isn't physics about something else? Isn't physics concerned with a different kind of question, namely, what is the world like? Instead of what will I see next? Well, in many cases, you would think that this is true, but then quantum theory has given us a different perspective. In quantum theory, we know that in some sense, unperformed experiments have no results. So when you go into situations like this one, an so-called Bell experiment, then there's Bell's theorem, and Bell's theorem tells us that the data that we see in such experiment, for such data, it's really inconsistent to assume that the measurements that the two parties have done has just told us what the world has been like before the measurement. It's just inconsistent unless we give up locality. So in many cases, the question that we ask cannot be interpreted as asking what is the world like or what has the world been like before we measured. And instead, we can really phrase it as well in such an experiment. What's the probabilities of what I will see next? So even physics tells in some sense, at least quantum physics, that what will I see next is in some sense the natural question to ask, or a more natural question to ask in some contexts. Good. Now, where to go from here? My suggestion is that we should try to come up with a different approach. And let me give you, again, this slide here with the problems to tell you conceptually what this approach could look like. So my approach would be to say this question, what will I see next, should have a unified approach that applies to all regimes at the same time. So you would want to have an approach or perhaps a theory that allows you to find an answer to this question, no matter if you ask it in the empirical regime or if you ask it in these exotic thought experiments like the Boltzmann brain problem. This approach could look like this, for example. You say, well, what I want is, I want some kind of probability rule of what happens next, given what's happened before. So what I will see next can be conditioned on what I've seen before, and I want to put some probability on that. So this would be, and I'm now trying to show you one way how you could try to do this, okay? This would be, in some sense, a reversal of the standard view. Here's, in some sense, the standard view that we take. You would say, well, that's our physical world. The physical world evolves in time according to certain laws of physics. Now, we are simply part of that physical world. So whatever we see can just be derived from basically taking some part of that physical world, and then we see, oh, here's my chair, and here's the window that I see. So we think that our state follows from the state of the world. So what I mean by state here, by the observer state, we're now observers. We're in some state, so this means everything that you see now, everything that you may remember consciously or unconsciously, basically your state of all locally available information that you have. And we think that just follows or is part of the physical world, and it changes over time in accordance with the state and the evolution of the physical world. Now, it is certainly true that this picture is correct, at least approximately in most instances. But I should first say, well, for the state of the observer here, for what I'm saying now, it doesn't really matter what these states feel like. So the notion of the question of qualia or of free will or of consciousness is not really relevant so much for what I'm saying in the following. Anyway, so the usual view that the state just follows from the state and evolution of the world, that helps us to make good predictions in the empirical regime. But the problem is that this view doesn't really help us to tackle the exotic puzzles that I mentioned earlier. So it seems questionable to say, well, if I just find out enough details of my teletransporter, what it's made of and how the molecules are arranged, and then I can work out whether I end up on Earth or on Mars, I don't think this can hold up. So there must be another approach. And the approach that you can do, at least you can attempt to do, is to say, well, let's reverse the view. Let's say that the laws, the fundamental laws, whatever they are, they apply directly on the first person, on the observer state. So you do this by giving up this idea of this underlying physical world, and you begin by just working with you as an observer, whatever that means, and your state, and say there's a law that applies directly here. What would that be? Well, it would be some probability rule. It tells you what your state will be next, given what it is now. So given all that you know, given all that you see, given all that you're made of, that you're not consciously aware of perhaps, there should be a probability rule that tells you how that changes to the next moment. Now, my proposal here for such an approach, as a kind of first model to see how that could work, is to use a law of induction for this probability. So to say, well, in some sense, the probability is higher for next states that are that you would actually predict if you were a good induction machine, a good prediction machine. So I'll get to that in a minute, what that would mean. Whoops, I'm sorry, that was the wrong button. Okay, now what you can show, and this is quite surprising perhaps, is if you do that approach and if you use the probability law that I'm postulating here, and my next slide will be on that probability law, so bear with me, then you can show as a theorem that in the long run, after you've made a couple of observations or gone through a couple of states, things will pretty much look as if there was an external world of which you're simply a part of. So in other words, you kind of recover the usual view that we have on our physical world as a very good approximation. Now, how would that work? What is this law of induction? So basically the claim here would be that what we call the external world is in some sense a statistical phenomenon. That's not fundamental, but that's emergent in some sense. So what's this law of induction here? This probability rule that applies directly to the observer. So there's a very colorful explanation. Just imagine that you've thrown this robot here into some environment, some unknown environment. And this robot is now trying to, go around, take measurements, and try to predict what's happening next. And universal induction is a tool or a mathematical tool from information theory that tells you what would be your best guess for the next data given the previous data that you recorded. So perhaps your previous data is that you've taken a lot of pictures of this planet and you've done some temperature measurements, and then you decide what next measurement to do. And then there's a certain method that allows you to put a probability on what you should believe about this. Now, where does this come from? This is called Solomonov induction. So this is a theory that's worked out by Ray Solomonov in the 60s, which gives you a method of universal induction, which is basically based on Occam's razor, that simple hypotheses are more likely than complex ones. So he defines some probability distribution mathematically by saying that the possible next data that you want to guess is more likely if it's more compressible given your previous data. More compressible, if you think a bit about your computers, means that it has more regularities. So given what you've seen before and the regularities that you may have encountered, you will bet on next data that reproduces these regularities in some sense. That's Solomonov's probabilities. My approach here is now to claim that there is actually a law that applies to the observer directly, and it's given by Solomonov's probabilities. Good. Now, what would that entail? First claim is that this is actually consistent with what we know about physics. So when you think of the empirical regime and the experiments that you build, then it turns out that the predictions that you get when you use Solomonov's probabilities, like I claim here, they are actually equivalent, at least asymptotically, to that what our physical theories tell you. And that's the case basically because there's some notion of a Church-Turing thesis, which tell you that the physical laws are computable in some sense. And that's enough to guarantee that you get consistency with physics with Solomonov's probabilities. So this is first consistency with physics, but then you can even show more than that. You can say that, well, after a while, this law of induction leads to a phenomenon that some kind of regularities that you had for a while will in some sense stabilize themselves after a while and give you the statistical impression as if that what you see came from some kind of process in which you're embedded. That process would be something like an external world. So you can show as a theorem that for observers that are described by this probability rule, it just will asymptotically look as if there was some kind of external world in an abstract sense, which is probabilistic, but it's simple, also algorithmically simple. So you can write down its behavior in some simple equations or computer code. But nevertheless, this world will look complex when you look at it. And it may also display some of the characteristic features of quantum theory. So that is something that you can prove when you ask what happens when I just make this claim here on the left-hand side. Now note, however, this is really not a theory of everything that I'm proposing. So this is not something that can tell you what the exact laws of physics could be, or So it's an approach that tells you, in fact, nothing about most things in physics, but it tells you a few things it does tell you, namely that things look as if they came from some simple process in which you're embedded. Okay, but now, so far we've seen consistency with our usual view of the world, but certainly what you can do now is you can try to apply this to get predictions in this more exotic regime. Like here's a very exotic regime. We ask, well, suppose I simulate some agent on a computer, and there are thought experiments by philosophers like Nick Bostrom. We say, well, maybe I want to find new medication, but I don't want to test it on actual humans. So I simulate some humans on my computer and test the medication on them. And I do the simulation really exactly and accurately. So if I do that, and some simulated being gets hurt, does this now cause any actual suffering? So how would you phrase this question in that context? Well, you could somehow say, well, what about the simulated being? Let's just look at its state, and let's use Solomonov probability of seeing whether its next state will be a state of pain, yes or no. That may be a different probability than that's going on in a simulation, or maybe the same one. It may also depend on your choices of how you program the simulation or not. And then you can try to work out what kind of consequences it has to run your simulation or not. In fact, in this case, you find that it differs very much whether you intervene in the simulation or not. So if you intervene a lot in the simulation, then you shouldn't do this. That's a short version. But if you just let a simulation run, then it's more like letting a movie run, and then you're not actually causing any actual suffering in some sense. So this is, well, these are the kind of predictions you can at least try to get in principle when you make an approach like this. Okay, good. Now, so far I've really just talked about a single observer. Yeah, think of this picture where you just see your own legs and you want to predict what will I see next. But certainly we believe that we are not the only observer, and there are others in the world around us. Now, let me tell you how an approach like this can have an emergent notion in some sense of objective reality. Quick question, how many more minutes do I have? 3.
Do your thing. It's very interesting.
Okay, good. Now, so what do we have so far? So far we've talked about a single observer. Let's call her Alice. And we've seen that if she's subject to this probability law, then she will make observations and experiences that look as if she was embedded in some kind of world. So perhaps it's a world like this. Yeah, we have to jump around and collect points. This is a world. This is Alice's world. It's a world that evolves probabilistically according to certain simple laws. Now suppose that in a world, Alice spots something where she said, aha, this thing over there, that pretty much looks like another observer to me. So what would that be? Well, we'd say, here's in my world, here's some random variable. That random variable, perhaps it's a string of zeros and ones or whatever you want to choose and pick. That could actually be the state of an observer or describe the state of an observer. Now you can ask, well, but does this random variable B, does this really faithfully represent some first person perspective? Should I think of like somebody really being there? Now, how would you formalize this? You can in such an approach. Well, I would say you have two probability distributions. First, you have a probability distribution, the third person probability law, that tells you for Alice in her world, when she looks at that other thing, how will that other thing change over time according to the laws of Alice's world? But certainly, you can just think of some first person that would be in the corresponding observer state, and ask what are the first person probabilities that if you are in that observer state, that something will happen to you. And this is Solomonov's probabilities, as I've just postulated before. So this is Solomonov algorithmic probability P, and it's like a first person probability. Now, a priori, in such an approach, these could be different things. So let's look at a simple example. Suppose in Alice's world, there every morning the sun is rising. So in the evening, Alice really believes that there is a 99% chance that she sees the sunrise tomorrow. Well, then Alice will see about that Bob thing over there that's sitting there that also has a 99% chance of seeing the sunrise. Yeah. So Alice also has a 99% chance that she will see Bob see the sunrise. But you can ask, now, what are Bob's actual chances of seeing the sunrise? So you think of one is the third person probability, the probability that Alice assigns to the Bob that she sees seeing the sunrise. And then there's the first person probability of Bob actually seeing the sunrise. Yeah. And now you can prove the following theorem. As long as that B thing over there keeps accumulating enough data and doesn't forget too much what he's seen, the first and the third person probabilities are extremely close to each other. They are just basically the same. So the answer to the question is yes. In this case, Bob will also have a first-person probability of 99% of seeing the sunrise. So in some sense, this A world where Alice finds herself to be in is also B world. It's also a world where Bob could say that he's embedded. But in an approach like this, you get a situation where this just doesn't apply. So like every theorem, which here tells you that these distributions are similar or the same, there are some things that have to be satisfied for it to be true. And it's not true in all cases. So do you find is that in some cases, the first and third person probabilities differ. And one such case is indeed the Boltzmann brain problem that I've talked about. You find that the probability that you think that this fluctuation out there in the universe should see something is not actually the probability that that thing sees something. And that's a way to kind of cure this Boltzmann brain problem. It's also true for some computer simulations. And it's the case if if that observer B is destroyed in A world. That would be a case of death, for example, where P first and P third could differ, perhaps. Good, so with that, let me conclude. I've told you, tried to tell you and argue that there are some conceptual puzzles in and around physics that motivate an approach to study the question, what will I see next in a unified way? And I've shown you one approach, like a blueprint of a kind of theory that tries this. And maybe since I'm running out of time, let me just refer you to the paper that I've published on that if you want to know more details, and stop here. And thank you very much for your attention. Thank you.
Amazing presentation, Markus. You probably have the most intriguing message of any physicist alive today. I've noticed, of course, that since from the very beginning you've tried to distance yourself from the philosophical implications that this message might have. I think that's entirely legitimate. Any serious physicist should do physics and leave the philosophy for others. I am, however, a philosopher, so I'm very interested in the philosophical implications of your message. So I have this question. According to you, the seeming external world is an emergent phenomenon which arises from inferential induction, from the attempt of the observer to infer what's going on out there. And your very first cartoon also suggested that our own bodies are part of this emergent external world. If I look down, I see my legs. My legs are part of the external world. They are made of the same atoms and force fields that we think constitute the world out there. So now my question is this. If my body is part of this inferential external world that's not really there, it's a product of the observer's mind trying to make sense of what's happening, then my body too is the result of a mental inference. It too is emergent. And then there is very little else that the observer could be other than mind. So philosophically speaking, isn't it a direct implication of your position that mind is primary in nature?
Well, you can view it that way to some extent, I would guess. But when I think about the observer state, then I'm thinking of structure in a kind of mathematical way, right? So basically, I want to some extent to be agnostic as to what the essence of that thing is. As a physicist, that first of all, I want to say, well, here is how I model it. And the way I model it, at least it presents itself in a way that we see it's not really the matter that you're made of. It's more the structure, perhaps like the way that your brain is connected and so on. And then you try to say, well, does it matter, for example, how you describe that structure? If you choose a different description, then your theory shouldn't change. And you kind of prove theorems around it where you say it doesn't really matter how you think of it. So it's in some sense the opposite what you want to do there. But yes, it's one step away from the usual, I would say the usual materialist worldview is not the one that applies here. But I would say I'm also not the first one to think of it in that way, because when you're a quantum physicist, then the wave function and the way you think of it is anyway far removed from the usual material picture of chairs and tables and so on, right? So in that sense, I would say this is already a view that's further spread, and where I'm not the first one to take this view.
I applaud your scientific rigor in remaining agnostic of philosophical questions. I'm sure Bernard has a question.
Yes, thank you, Marcus. I'd like to ask a rather general question. You were focusing very much on what will I see. But the thing about physics is that it often talks about things which can't be seen. So you talk about what goes on inside a black hole, which you can't see. You talk about quarks, which you never see. You talk about multiverses, where you never see the other universes. And you talk about extra dimensions, which you never see as yet. And I suppose other people's consciousnesses are examples of things you don't see. And yet, in some sense, physics does seem to involve things you can't see. And to my mind, that in itself is perhaps supports a sort of idealistic philosophy, because you can't see them but materially, but in some sense they're creations of your mind. But you've taken a different approach. You're coming to an idealistic philosophy by focusing on what you can see. And so I'd be interested if you could address that sort of rather almost a paradox.
Yes. So I would say that in an approach like this, you have things you see, but then you also have probabilities of what you see next. And in this case, when you want to talk about the probabilities of what you see next, where things come into play that you would not see directly, yeah? And where you can show that there is this idea of this process that you're part of, that you're not usually seeing directly, that you might call your external world. So that's really just a mirror image of what we do in physics anyway. So we make claims like we have curved space, we have something that goes on in the sun, and make other such claims, so that in a way it reproduces, it allows us to explain what we really do see on our measurement devices later on. And it doesn't do this explanation in an arbitrary way. It's not an arbitrary explanation, but some kind of economic explanation, a simple one. Right? And this is also reflected here in the use of Solomonov probabilities, that you say, well, I'm part of this process, but it's a simple process, and it generates what I see. Right? So, yeah, I would say that my use of invisible things or invisible processes is not much different from the way we have it in physics anyway.
Does this mean that you're more or less skeptical about concepts which, such as extra dimensions and other universes, which can't be seen? I'm trying to work out what your approach is to that part of the issue.
Well, I think I just share the same skepticism or non-skepticism with most of my colleagues. So I put a high stakes on things that we don't see, but think we have lots of evidence on, like black holes, what's happening inside the sun, galaxies that are perhaps beyond our view, and so on. Now, when you ask me, what about extra dimensions? Well, I don't know. As far as I know, we don't have experimental evidence for them, but I'm also not an expert in string theory. And I think this kind of view is shared by my colleagues as well, who have other worldviews, right? So this doesn't differ in that sense.
I guess what is not seen today, though, may be seen tomorrow.
Yes, sure, yes.
Markus, clearly you are not a solipsist. You acknowledge that Bob exists in Alice's world, and you acknowledge that Bob is also an observer that infers an emergent external reality. So there are more than one observers around. Doesn't that imply that there has to be a shared ontic existent context that both Alice, Bob, and other observers inhabit? And in that sense, there is some kind of world they inhabit, even if it's not a physical world, in the sense of not being a world describable through defined physical constants.
So in some sense, that's exactly not the case. So the way I define an observer state is a standalone abstract thing. So that goes away from our usual picture that what is me is, this thing here, but also that thing in that world and not the same thing elsewhere. Yeah. When we think of the Parfit's shared paradox. You'd think, well, I am now the guinea pig on this planet and not the identical guinea pig on the other planet. But I'm denying this. I'm saying I'm only that structure that's here, and everything else around is not ontologically fundamental. But there is certainly a certain ontological claim at the bottom, but it's a bit harder to imagine. Just to give you an example that you may know, so that you see how it could be, is when you know the movie Back to the Future. Yeah? In the movie Back to the Future, you have Marty McFly who travels into the future and then meets his future self. So he kind of hides in the garage and sees that his future self is coming around the corner. Now, are these now two different observers or one observer? Right? No idea. So in some sense, it depends on what version here you put. But in that approach, one way possible interpretation would be like the other observers that we see is just it's also us, but much later and combinatorially long time in the future. Now, forget what I'm said again, but I just want to show you like that the ontology that kind of presents itself here when you take this approach seriously is very unusual in some cases. Yeah.
Yeah, I think the philosophical implications of what you just said are profound, and there is nothing I would like to do more than to continue to discuss them. But unfortunately, we are out of time. Markus, thanks a lot. It's been a fantastic and inspiring, very intriguing presentation.